Okay, I'll get started. Yeah, thanks. I think it's good that this problem for yes, state how much time you spent on the P set. It's good I put that in there because I think next P set I have to make not as long. I was skimming some of those answers and yeah, sorry about that. Oh, 1B, is that? Yeah, I see. Okay. No, actually, there's a way to get there's a way to get a really short answer to 1B, which I guess we'll put in the solution section. No. Okay, so today I want to talk about online algorithms. Is this the right word to be writing on? Yes. Okay, and this is all about making decisions in the face of uncertainty. So I'm going to imagine there's an input, which is a sequence of requests. You're going to see some examples. And I don't know the future. I just know the requests I've seen so far. And based on, and let's say there are many ways to satisfy this request. And I have to make a decision about how I'm going to satisfy it. Okay? And I want to make these decisions in such a way that I don't regret the decision. Like in the future, when I look back at what I decided, I don't want to regret things too much. Okay? So we'll see. We'll try to formalize this. Okay, so there is some cost to making a decision. Cost paid for making, say, a certain decision. And at the end of the day of the sequence of requests, do we have a scribe, by the way? Okay. We want to make sure, want to say, we didn't spend much more than some omniscient being who knew the future at the beginning. Or spend much more than the best in hindsight. Right, so let's say you're working on Wall Street or something, or you're managing the investment portfolio of Harvard or somewhere else, and the amount of money you made this year is much less than the amount of money that the person who had your job last year made. So now they want to fire you, right? And you want to say, look, it's true I made less money, but this year is a different year than last year. This year the best anyone could have made, even if they knew the future, is much less than what you could have made last year, and I was competitive with the best I could have possibly done. So you could use this kind of thing to save your job. Okay. So, well, okay, you can use it for also more real applications. You'll see that later in class. Okay, so let's formalize this a little more. So we run some algorithm A to make decisions. And opt is an algorithm making the best decisions while knowing the future. Okay. And then the definition, we say that we say A is let's say R competitive if for all request sequences, sigma, which is sigma 1, sigma 2, sigma m, let's say, the cost using A to serve sigma is at most R times the cost of opt to serve sigma, maybe plus some additive term. Okay. And this is called competitive analysis. Okay. And it was introduced by none other than Slater and Tarjan. Totally different paper than Splatry's, but the same year. At least the journal versions are the same year. I can't remember about the conference versions. Okay, so before I look at, so today we're going to look primarily at the paging problem. I'll define that later in lecture. But before I define that problem, I want to give you, I guess, two toy examples. Okay. I think if people were in CS 124 with me last semester, I mentioned one of them. I'll just refresh your memory. Yeah, I don't. It's okay if you weren't in there last semester. You'll see it again. So one classic toy example. So toy examples. So one is what's called the ski rental problem. People always start off online algorithms with this thing because it's simple enough to demonstrate what's going on. So the only thing that's unknown in the ski rental problem is m, the length of the sequence. So what's going on? So you imagine that you and your friends are at a ski resort, and they didn't tell you how long they want to spend on this vacation. But you're willing to spend as long as they tell you, okay? And each day they'll wake up and they'll either say, okay, we're done with this vacation, we're going home now. Or they'll say, we want to stay one more day, okay, and ski. And if they stay one more day and ski, you have to have skis to go out skiing with them. Okay, so you can either rent the skis for the day, that costs $1, or you can choose to buy skis, which costs $B. Okay, so each day must either rent skis $1 or buy skis, that's $B. And of course, once you buy skis, you never need to rent them in the future. You can use them on all future days for free. Okay. So the question is, what do you do? Right. So if you want to look at opt knows the future. What does that mean here? It means opt knows when your friends are going to say, let's go home. Okay. So what would opt do? Yeah, otherwise rent every day, right? So opt says if number of days greater than B, buy skis, else rent every day. Right? But we don't know the future and we want to be competitive with this. So what do we do? Yeah. So us, rent for B days. Buy skis on B plus first day, if there is a B plus first day. Okay, so if the number of days we spend at this resort is at most B, opt paid the number of days because it rented every day, and we also paid the number of days because we also rented every day. If we stayed for more than B days, then opt would pay B, we pay at most 2B. Okay? So this implies that we are too competitive. We never spend more than twice the amount of money that opt spent. I think maybe you might even do slightly better if you rent for B-1 days and buy on the Bth day. I think you get very slightly under 2B. But if B is large, it starts looking like 2 anyway. Okay, so that's one example. Let me give you one more toy example before I get into the main parts of the lecture. So toy example 2. I'll just call this free pizza. Okay. I don't know, what's a building in Harvard that has a really long hallway? Are there any such buildings? Oh, that's not. Okay, so I don't know. So let's say that there's a building that has a really long hallway. And there are rooms on one side of it, evenly spaced. There's room 1, 2, 3, up to n. And you're standing here. This is right in front of room, n over 2. Okay. And you heard from one of your friends that there was free pizza. There's some recruiting event. One of these rooms has free pizza, but you don't have signal right now, and you can't text your friend, and there's no Wi-Fi for some reason. So you just need to find this pizza. Okay. So I mean, you could. It's in one of these n rooms. So what do? Right? Opt knows where the pizza is. Right. So opt would just go straight there. You don't know. It could be to your left or to your right. Okay, but you want to make sure that you don't spend that much more time walking than opt would spend. Okay, is the situation clear? Okay, so what would you do? Zigzag, yeah, exactly. So when you say zigzag, what do you mean?
Go left and check the first room, right on your left, and then check the room.
So check this room. Then go back, check that room. Okay, and then now go to this room and then go to that room, like this? Like this?
After checking the first right room, you can check the right to your.
Oh wait, say it again.
After checking the n over 2 plus 1 room.
Yeah, after checking. So okay, let's go back. So I'll first check this room. That's my first thing to check. And then where do I go? Go left 1. And then?
Go left 1 more.
Okay.
And then go forward.
And then I go forward?
Yeah.
So check this next. Yeah. This is the 4th room I check?
Yes, that's my case.
So I guess, is there a way to describe, let me, just to make this picture clearer, let me just call this 0. And let me call this room minus n over 2. And let me call this room n over 2. Okay, so you're zigzagging, you're going back and forth, and what's the property you want from your zigzagging? Like in the kth zigzag, roughly how far to the left or right are you going in the kth zigzag? I don't know if I said that.
K. What do you mean K?
So you're going to go left some number of steps, then you're going to zigzag and go right some number of steps, then you're going to go left some number of steps, right number of steps. So let's say you're in the kth phase of this. So how far do you want to go as a function of k? Twice the amount before, roughly 2 to the k. Yeah, so let's look at that. So visit rooms 1, then minus 2, then 4, then minus 8, then 16, etc. Okay, so in reality, let's just say that let's say that the room we actually want to go to is t. It could be minus t. The analysis would basically be the same. Let's say pizza is in room t. Then, how much walking do we do before we find room t? First of all, opt will spend t time walking there. Whereas we'll spend, so opt spends t time. We spend time, which looks something like 1. So we pay 1 to go to 1, then 1 to go back. Then we pay 2 to go to minus 2, and then 2 to go back, etc. Until finally we pay 2 to the m plus 2 to the m. And then finally we get there in our t steps. Okay. And the worst case is that this 2 to the m here, I guess, will be something like at most 2t. Okay. Or maybe even t. Because we could be going in the wrong direction here. And I guess it would be, so before we didn't hit t before, which means we were going less than t before. Yeah, so this 2 to the m here is certainly at most 2t. Okay. And then we have this geometric series, which sums to something. So let's say this is at most t plus 2 times 1 plus 2 plus 4 plus dot dot plus 2t, or some power of 2. That's at least t. This thing here is at most 4t. 4t times 2 is 8t plus t is at most 9t. Okay, so opt spent t time, we spent 9t time. So this is a constant competitive algorithm, a non-competitive algorithm. Okay. Okay, great. So those are just 2 toy examples to make you feel comfortable with. Yes.
So when you say visit rooms 1 minus 2, does that include all the ones?
Yeah. So as you're walking there, you're going to peek into every room that's along the way.
So it's 1 minus 1 minus 2.
Yeah. So so you walk toward 1, then you walk toward minus 2, but then you peek in every room along the way. Then you walk to 4, you peek in every room along the way, etc. Let's pretend peeking in a room, once you're in front of it, you can just look into it without paying anything.
What's the cost of campus police arresting you looking crazy?
Yeah, that could slow you down, I guess. But let's say there's no police, to simplify the analysis. Okay, good. So, so Slater and Tarjan, I said, introduced this competitive analysis, and they were not concerned with ski resorts or free pizza. So, what are the things that Slater and Tarjan looked at? So they looked at 2 problems. The first problem they looked at was the list update problem. I'll define it. And 2 is paging. And I'll formally define these. But the basic idea behind them, I'll just say right now. With this problem, you imagine that you have a linked list. Okay? And you have repeated requests to access items that are in this linked list. Okay? So if the item that you're told to access is the ith position in this linked list, it costs you I steps to walk there. But once you access it, I'm allowing you for free to move it anywhere earlier in the list, anywhere that you already walked past. Okay. So you're allowed to change you're allowed to reshuffle things in your linked list. There's also insertions into the linked list, which just puts it at the end. But then also after you put it in the end, you can move it anywhere forward if you want to. And there's also deletion. And paging is, it's going to be about basically 2 levels of memory. So you have some fast memory, and then you have something slow like disk. Okay, or you have, say, cache versus RAM. And cache, let's say, has some bounded size. And when someone asks for some location, if it's in cache, you just fetch it. If it's not in cache, you have to bring it in from memory. And you have to pay to do that. Okay. But if cache is full, you have to evict someone from cache and send it to memory. So you'd like to minimize the number of evictions. Okay. Well, we'll see. I'll more carefully go through both of these. Let me start now with list update. So list update. There are n items in a linked list. 3 operations. There's access x, insert x, and delete x. Access x just means you have to touch item x. Okay, and your pointer starts at the beginning of the linked list. Insert means put it at the end. Delete means remove that node. After accessing an item, allowed to move it anywhere closer to the front of the list. Okay. And let me say here, accessing the ith item costs I. So I'm not going to mention all the things that came about before Slater and Tarjan, but I will say for a while there were many papers analyzing various heuristics for this problem. So let me list some of the heuristics that people looked at. There's the move to front heuristic. I'll call that MF, which says always move the accessed item to the front of the list. There's also the transpose heuristic, which says transpose accessed item with the previous item, with the item before it, immediately before it in the list. Okay, so it's a less extreme version of move to front. Right? Move to front jumps it all the way to the beginning. Transpose just gradually moves it toward the beginning. Right? So if you keep accessing it, it gradually walks forward to the front until when you access it enough times, it's at the front. And then there's frequency count, which says keep items in sorted order by frequency of accesses, most to least frequent. Okay, so for each item, you keep track of how many times so far has someone requested this item. Okay, those are the frequencies of the items, and you make sure that the most frequent items are toward the front. Makes sense. And kind of so right before Slater and Tarjan, there was a paper by Bentley and, I don't know how to pronounce it, McGeoch, I think. But before that paper, there were lots of papers analyzing these heuristics, trying to explain why they might behave well in practice. And those papers were all like probabilistic. They tried to create probabilistic models for what sequences might look like. And then they showed that under this probabilistic model, such and such heuristic does well. Okay, they proved theorems like that. The first worst case analysis that tried to understand these heuristics was by the paper I mentioned. So worst case, there was a paper by Bentley and McGeoch, I think. This was in '85. And they proved a theorem. Okay. They said, first of all, they said no, there are no insertions. If there are no insertions, and I think the items need to start off sorted by order of first access. If no insertions and the items are initially sorted by time of first access, then the cost, say the cost of move to front, I believe is at most twice the cost. Then for all sequences, for all access sequences S, the cost of move to front on S is at most twice the cost of frequency count on S. Okay. So that, okay, so this says that move to front is not that much worse than frequency count. And they also did some experiments, and they found that frequency count did well on their experiments. Move to front did usually just as well, sometimes better, and transpose sucked. Okay. Now, I want to say that I want to compare this inequality to the static optimality bound we proved about splay trees, right? So what was the static optimality bound saying for splay trees? It said that splay trees do, on any sequence of accesses, splay trees does as well as any fixed tree, where that tree is not allowed to do rotations and adjust itself. Okay. Now, this is basically the same thing for this list update problem. So if you're not allowed to do any moves of items, right? So I said after accessing an item, you're allowed to do some rebalancing, like in splay trees. You're allowed to do some movements in the linked list. If you're not allowed to do any movements, then the best thing to do is frequency count. Okay, frequency count will minimize the total time to serve the whole access sequence. So this is like a static optimality theorem for move to front. So this is like static optimality. For move to front. Okay, but as we saw with splay trees, there is this dynamic oh yeah?
So if the items are initially sorted by time of first access,
Yeah.
then how can you keep them sorted by frequency without moving them around?
Right, so actually that's a good point. So this is even better than a static optimality theorem, right? So I think, because certainly then I think we're better.
Does frequency count here mean like by the overall frequency across the entire sequence if you know the full sequence, or does it just mean by frequency thus far?
So yeah, that's a good point. So here frequency count means we might move items if their frequency changes. Yeah, so here we are changing. So I have to think, the question is, do we do only better by updating the frequency count as things go along, right? So is this only better? So yeah, maybe I understand your question. The question is, if you do frequency count where you're allowed to move around items versus frequency count where you're not allowed to move items, is the first always strictly better than the second? I'd have to think for a moment about that. I don't know. If so, then yes, you would have the static optimality theorem. Okay, but we're going to prove something even better than static optimality anyway. Okay. So with splay trees, there was the dynamic optimality conjecture, which says not only are we better than any fixed tree, but we're also competitive in this, well, I erased it, but in this competitive analysis notion of competitive ratios. The conjecture is splay trees are competitive even against trees that are allowed to rotate. Trees that know the future accesses and rotate themselves to be just as fast as possible to serve everything. So the question is, does move to front or anything else satisfy dynamic optimality? And the answer is yes. So theorem, due to Slater and Tarjan now, is that move to front is dynamically optimal. And by that, I mean that the competitive ratio is a constant, independent of n, let's say. Okay. So so what do we need to prove? We will prove the following. So the claim, I'll write it and then I'll define some notation. So first of all, actually, Slater and Tarjan in their proof allowed even more things to happen. So move to front doesn't take advantage of this, but they said, look, after accessing an item, you can move it anywhere forward for free. They also looked at a model where not only can you do that, but you can always pay one to just move to transpose items. Okay. So if I have an item and I want to transpose it with the person right before it, I can pay one to do that. Okay. Move to front doesn't take advantage of this, but you could ask yourself, well, maybe if I could take advantage of this, I could do even better. But no, they say let A be any algorithm. Then for all access sequences S, the cost of move to front on S is at most twice the cost. And let's say that S has M operations. The cost of A on S plus the number of, they call this paid exchanges that A makes. So paid exchanges means you pay one to do the transpose with the predecessor, minus the number of free exchanges, minus M. So free exchanges look like this. Paid exchanges are we swap with your predecessor. Oh, and I should say, I mean, if I don't say the next thing, then this is going to be trivially false. We assume that at the beginning of S, A and MF have all items in the same order. Right? If you want to prove a theorem like this, then the linked lists that A has and the linked list that MF has better had, start in the same order. Questions about the statement of the theorem before I prove it, like what anything means? Okay. So we'll prove this using a potential function argument. Phi equals the number of inversions in MF's list using the ordering specified by A's list. What I mean by that is, if you have an item, so here's MF. Whenever you have a pair of items such that I appears before J in MF, but I appears after J in A, I call that an inversion. Okay. Okay. So now let's look at the cost of an access, the amortized cost of an access. And let's also remember that total cost is equal to the amortized cost plus the initial potential minus the final potential. Okay. Well, potentials here, as I've defined them, are always non-negative. So this is certainly at most the amortized cost plus the initial potential. And the initial potential is 0. There are no inversions at the beginning because they started with the same ordering. So really, we just need to bound the amortized cost. Okay. So what's the amortized cost of an access, say access X, so remember, amortized cost is actual cost minus the potential difference. Okay, so let's bound this thing. Suppose X is ith item for A, and it's the kth item for move to front. I mean, in their respective linked lists. So the actual cost is then K, right, to search for it and move to front. Now, how about the difference in potential? Suppose there are, let me make sure I don't confuse myself. Suppose there are T items that are before I in before X in MF's list, but after X in A's list. Okay. And now what does MF do? MF takes X and it moves it to the front of the list. So it changes the status of inversions. It creates some new inversions and it kills some of the old inversions, right? So how many, just to make sure we're on the same page, how many inversions does it undo? Yeah, it undoes T inversions. And how many new inversions does it create? Right, K minus T, is it K minus T minus 1, I think. K minus T minus 1 new inversions. Right, because there were K minus 1 items before it. And yeah, so and T of those were inverted, and the other K minus T minus 1 aren't. So that implies that the change in potential is equal to k minus, let's see, so k minus t minus 1 minus t is equal to k minus 2t minus 1. So that's k minus 2t minus 1. So this implies that the amortized cost is 2k minus t minus 1. So what do we really want the amortized cost to be if we want to be competitive with opt? How much does opt pay? So A, to be competitive with A. So we're imagining A is opt, right? We're saying this is true for all A, so in particular it's true against the optimal A. So how much would A pay in terms of variables we've already set up there? How much would A pay to serve this request? Or does A pay to serve this request? I. It pays I, right? So for us to say we're competitive, one way to do that is to say, look, the amortized cost of every operation is roughly I, right? So why is this thing at most roughly I? Yeah. Yeah. Yes, there are I minus 1 of them. That's right.
And we said there are k minus t minus 1 before x MX lists initially
That are not inverted. Yeah, exactly. That's exactly right, right? So what do we know? We know that these k minus t minus 1 items, okay, are before are before x in both the MF list and A's list, right? But how many spots are there in A's list before x? There are only I minus 1 spots. So then this definitely needs to be at most I minus 1, which means this is at most I. So this is at most 2I minus 1. Okay? So when you sum up amortized costs across all operations, you're paying proportional to, you're basically proving the theorem, right? So that's this factor of 2. And this minus 1 is that minus m. Now, what about when you do a free exchange? So at some point, what is a free exchange? That means after you touched an item, you move it forward 1. Okay? Well, move to front, moved it forward all the way. If you move it forward 1, you're decreasing the potential by exactly 1. Okay. What if you do a paid exchange? Well, you're at most increasing the number of inversions by 1. Okay, so that's it. So that's the proof of the theorem. Okay. So that's moved to front. Now, I mentioned they also looked at paging. So paging is going to be an example of this list update problem with a little, with a twist, I guess you can say. So what if accessing ith item in the list costs f of I and not just I? So f of I equals I is this problem we just looked at, but in general there could be some other function of I. Okay, and the paging problem f of I is equal to 0 if I is less than or equal to k, and it's 1 otherwise. What does that correspond to for us? I mean, why would I want to look at this f function? Well, let me show you what it's trying to capture. Oh, and paging also in the paging model, we require that when we access item I, if I is bigger than k, then we must transpose it down to some position which is at most k. So I'll come back to this, but let me tell you where this is coming from. So the setup is as follows. We have, as I mentioned earlier, we have this memory. So we have, say, k cache lines. And this is memory. And then we have some disk, infinite disk, divided up also into some blocks, which are the size of a cache line. And we have repeated requests for various pages. If the page lives in memory, I'll just give it to you. If the page doesn't live in memory, then it's on disk. I have to go fetch it and bring it into memory. And then I give it to you. And then if you ask for it later and it's still in memory, I can give it to you for free from then on. So fetching from disk costs us 1. Okay. But sometimes when I fetch from disk, memory is full, in which case I have to choose one of these k pages to evict. And I'll evict it and then put my page in. But I have a choice, right? So this is where my decision making comes into play. And there were lots of heuristics out there for what to evict. So your cache replacement policy. Heuristics. So there was, for example, least recently used. Oh, right. So now that I've said the setup, right? So, right, these first k spots are exactly memory. Everything else is disk, right? So accessing memory costs 0. Okay, so there's least recently used. Okay. So I have a choice of what to evict. And I guess the name tells you what I'll evict. The page that was least recently accessed. What does that correspond to when you think about, you voiced it, I guess, or lipped it. Did you? Move to front, right? Least recently used is exactly move to front. There's also least frequently used. What does that correspond to? Well, I didn't tell you what it is, but it's what the name says. So you look at the page that's been least frequently accessed, and that's what you evict.
Least frequently accessed in all of history or since you?
Yeah, up until this point. Up until this point in history. Yeah. Okay, I guess maybe I'm asking questions that are boring you. Frequency count. This is frequency count. Yeah.
Isn't it not quite frequency count because you could be like have lots of pages, like lots of hot pages, and then you access one evict one of the hot pages, so you'll have like a bump in your distribution.
Oh, because I have to bring it in.
Yeah, because you have to bring it in. So the
Oh, I
last
see.
one,
That's true.
it's not quite frequency.
It's not frequency count. That's good. I think I confused myself. Okay. Yeah, that's because you have to bring pages into memory. Yeah, I think you're right. It's not frequency count. There's also FIFO, so first in, first out. So this is usually called FIFO. So this one, you kick out the page that was brought into memory the farthest back in the future. I guess it's also as the name suggests. Okay. And in the Slater and Targent paper, there's one other one that they put in there, which I'm not sure. I don't know why people would use this heuristic, but it was something like evict the page that I most recently brought into memory. Why would I do that? I don't understand, but that was listed there. But anyway, okay. What do I want to say? So I want to say that, so the theorem that Slater and Targent proved okay, is that LRU and FIFO are both K competitive. Okay, it sounds pretty horrible. If your memory is, 8 gigabytes or something, I mean, it's a huge number, okay? Unfortunately, they also proved the lower bound. Any online algorithm cannot, so let me say no online algorithm just can have competitive ratio less than K. Okay, so proof, why is that the case? So if I give you an algorithm, right, and you're trying to construct a sequence, right? So what does it mean to have good competitive ratio? It means that for all sequences you behave well. So I'm saying that for any algorithm, there's a sequence that messes it up. So what's that sequence? So I have some stuff, K things in memory. Okay, let's say that total number of pages in the universe is K plus 1. Okay. So I have K of those pages in memory. What should the next thing in the access sequence be? The one I don't have. Then my policy will evict someone. And then the person I evicted, oh, it happens to be the next person in the sequence. Okay, so I'm going to have page faults nonstop. Okay. Meanwhile, what's a way? So let's look at what opt does. Opt knows the future. Okay. So what is opt going to do for that sequence? I claim there's always a way to guarantee that you never have a page fault more than every K steps, every K pages. Okay? Why is that? There's a way to guarantee that if I have a page fault now, my next page fault will not be until at least K steps in the future.
You evict the one that's going to be accessed K steps.
Farthest in the future, right? If I evict the person who's farthest in the future, then that means there had to be at least K things before him, right? So meanwhile, always request, so let's call this algorithm A, always request what A just evicted. Meanwhile, farthest in the future, only faults at most 1 in k steps, 1 in k accesses. So we're paying k times more than opt. Now you might think that this is trivial. Doesn't every algorithm achieve a competitive ratio of k, the memory size k? In fact, though, no. You can show that some algorithms, like for example, least frequently used, you can come up with a sequence where it has an unbounded ratio. Okay. For example, you can come up with sequences where opt is something like 1, and this thing makes an unbounded number of faults. That's basically the length of the sequence. Okay, so you can see the paper for that example, or I don't know, maybe I'll give some of these things as homeworks at some point. We'll see. Okay, so it's not that great, but let's prove it. And then I'll talk a little bit about how to circumvent this lower bound, right? I mean, we don't want to have an 8 billion competitive algorithm. What's the point? But it's not as bad as it sounds, it turns out. So what we'll actually show is that something I'll call 1-bit LRU is k competitive. Okay. What's 1-bit LRU? Well, let me describe what 1-bit LRU is. Okay. So initially, so let me say 1-bit LRU. Initially, all pages are unmarked. Okay. When an access comes in, when a request comes, if we must evict, then evict an unmarked page. Always mark accessed items. Okay, so whenever we access an item, we mark it. Whenever we access a page, we mark that page. And if we need to evict someone to make room, we'll make sure we evict an unmarked page. Okay. Now, eventually, everybody's going to be marked if we keep doing this, right? And the way that you evict an unmarked page is just arbitrarily. It doesn't matter which one you do. Just evict any unmarked page. Okay. Eventually, everybody will be marked. There's no unmarked page to evict. So what do? If all pages are marked when need to evict, clear all marked bits. Okay? And then now evict one of them and bring in the new page and mark it. So once in a while, we forget about who's marked. So 1-bit LRU is k competitive implies, oh, and one thing I should say, I'm not going to prove it in class, but there was a paper, so let me write this here, so I think it's Bilotti, maybe. There was a paper, so farthest in future could be another one. I mean, you can't actually implement it because you need to know the future. But you can show that this is always opt. So this was due to Bilotti and some IBM Journal of Systems, I think in '66. I don't think we need to use that fact here, but just so we know what opt looks like. So I claim that 1-bit LRU being k competitive implies that LRU is k competitive. Why is that? What's a one-line proof of that? Yeah.
The least reasonably used bit will always be clear.
Yeah, right. So in particular, so here in the 1-bit LRU scheme, all I say is evict an unmarked page. I don't specify to you which one to evict. I leave that up to the implementer. LRU is a particular way of implementing this. Okay. So, right, because when do I unmark a page? Basically, there had to have been, I had to have brought in k new people, and then a k plus first person came, right, to make me clear all the marked bits. So the least recently used person is always at least k in the past, right, which means he's always going to be unmarked. He's from the previous phase of clearing. Since LRU implements a particular approach, a particular way of choosing an unmarked page. Okay. So let me call a phase the point in time between clearing all the bits and the next time I have to clear all the bits. So we break sequence into phases. Let's say, is delineated the right word? By clear all bit operations. So as we move from phase to phase, what's a lower bound on the number of page faults made by opt? Yeah. Let's say we don't use you don't even use the fact that this is opt. Okay. How many distinct pages had to have been accessed for us to start a new phase? I guess I said it a second ago. It's k plus 1. Because we brought in k marked people, and then the k plus first person evicted one of them. Right? So even opt only has k pages in memory. So even opt has to have a page fault to serve these k plus 1 pages. Meanwhile, how many page faults does LRU have in a phase? It has exactly k, right? Because every time every time I have a page fault, I bring the number of marked bits increases by exactly 1. I bring a new person in and set his marked bit to 1, right? So within phase, LRU has exactly k faults. Opt has at least one fault. That's it. That's the end of the proof. So we're k competitive. Oh, I should have said 1-bit LRU, but as I said earlier, if 1-bit LRU works, so does LRU. Okay, so as I said, this lower bound is sort of, what's the point? If we can't beat k competitive, and k competitive is not really that great when you have a big memory, it doesn't sound too great. So I mean, one thing is, usually memory is not, I think, yeah.
Could you just explain why it's exactly k?
Sorry? Why it has exactly k faults? Okay, so how does a phase start? It starts with everybody being unmarked. Now, what happens when I have a page fault? When I have a page fault, I kick out an unmarked person and replace him with a new person who's now marked. So every time I have a page fault, the number of marked bits increases by exactly 1. And a phase ends when I have k marked bits, and then the new person comes in who's not there, right? So
You get a marked bit just by accessing the page without having a page fault. So for example, if you just
yeah, that's a good point. That's a good point. That's a good point. So the point was, if someone's already in memory from the previous phase and I touch them, oh, and I guess you said at most k. Most k is right. Oh yeah. So if someone was already in memory just from the previous phase and you didn't have to bring them in, now they're touched. Yeah, that's a good point. Okay. Good. So what's a way around the lower bound? So circumventing lower bound. So let's say 3 ways around it. The first thing you say is, look, oftentimes when people implement caches, et cetera, they're not fully associative. Okay. So they might only be partially associative, or not associative at all. If they're not associative, then there's really nothing for us to say. Partially associative means there's only, for any given page, there's only like a small number of places where it could live, and we'll put it in one of those. Okay. So the competitive ratio you get is like the associativity of your cache as opposed to the size of your cache, which might be smaller. Okay. But aside from that, one way to circumvent this lower bound is to do what's called resource augmentation. This was also introduced in Slater and Tarjan's paper. So give ourselves k memory, or k slots in memory, and give opt k prime, which is at most k slots in memory. So maybe I'm not that competitive against opt, which has exactly the same resources as me. But let's say I have k slots of memory and opt only has k over 2. Right? And now I ask, what's the best opt could have done with k over 2 slots of memory on this sequence versus what LRU is doing with k? Okay. And Slater and Tarjan showed that LRU and FIFO are actually k over k minus k prime plus 1 competitive. So I'm not going to show that modified proof here. But the point is, if you say, look, opt doesn't have k slots of memory, but it has k over 2, then I'm too competitive against that kind of adversary. So you limit the power of against that kind of omniscient being. So if you limit the power of the omniscient being by a little bit, you can get better competitive ratios. Another way to circumvent the lower bound is to consider randomization. By that I mean that the cache replacement policy can make random decisions. Okay. If you think about, look at the proof that you can't beat K competitiveness. Well, the adversary who's creating this hard sequence has to know what you're going to evict. But if the thing you evict is random in some way, then he can't make that sequence in advance. So we have to talk about what can an adversary do. So types of adversaries. The first is omniscient. By that I mean he knows everything. He even knows the random bits you're going to flip in the future. Okay. If he even knows the random bits that you're going to flip in the future, then you're really just a deterministic algorithm. And randomness doesn't help you. Knows all random bits, even in future. So randomness is not really going to help you against this kind of adversary. There's also what I'll call an adaptive adversary, which is a little more realistic. So this is someone who maybe has some ability to measure performance or measure things on your machine. And he knows the past. He knows everything that he's accessed so far. And based on that information, he decides what the next thing to ask is. Okay? So he knows the random bits you flipped in the past, but he doesn't know the random bits you'll flip in the future. So he knows past randomness, but not the future. And then there's the oblivious adversary. So this person is not trying to destroy your cache performance. Okay? They have some set of pages that they actually just want to look at. Okay? And they're not going to change their mind based on how things are going up till this point. Okay, so chooses access sequence S independent of, no, at the beginning. At the beginning. Before any coins are flipped. Okay. So I think this lower bound, says you can't do anything against an omniscient adversary, but it also says you can't do anything against an adaptive adversary. Because if the adaptive adversary knows the state of everything in the past, then he also knows what you don't have in your cache right now, and he can adaptively choose to pick that. But it doesn't say anything about oblivious adversaries, right? So theorem, this is due to, let's say, Fiat and a bunch of others. Fiat, Karp, Luby, McGeoch, Slater, and Young. No, there's no Tarjan. In 1991. And by the way, this I think I mentioned Bentley and McGeoch earlier. This is not the same McGeoch. So maybe they're related or married. I'm not sure. I think they're both at Amherst College, so they're probably connected to each other in some way. But yes, so what did they show? We can achieve, there is a randomized algorithm with competitive ratio 2 times the kth harmonic number against oblivious adversaries. Or remember, this thing means 1 plus 1 over 1/2 plus 1/3 plus 1/4 plus dot 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 plus 1 over k, which is equal to ln k plus up to some competitive constant. And also, any randomized scheme has competitive ratio, which is at least omega log k. So probably start trying to say something about this, but oh, how convenient, I boxed that. Okay, so I didn't say what the algorithm is. They call it the marking algorithm. Okay, and it's going to be it's going to be 1-bit LRU. But what do you think we're going to do to 1-bit LRU? Randomly what? Randomly evict. Yes, I'll just swap order the two words. Evict a random unmarked page. Yeah, but maybe they mean the same thing. I just want to make sure I'm yeah, okay, good. So 1-bit LRU doesn't specify how to evict the unmarked page. LRU did it according to being least recently used. The marking algorithm is going to choose a random unmarked page. The marking algorithm, I'll just call it M from now on. Evict an unmarked page in 1-bit LRU, chosen uniformly at random. Okay. And how does this go? So the claim is that M is 2HK competitive. Okay. Now, first of all, I guess I should probably define what I mean by competitive ratio for a randomized algorithm. Okay. Let me just define that. So definition, a randomized algorithm A, let me not put A twice. A randomized algorithm A is R competitive if for all sequences S, the expected cost of A on S is at most R times the cost of opt on S plus a constant. Okay. That's what I mean. So how does the analysis go? I have some number of minutes. I think it's short enough that it's possible. So proof of claim, or I'll at least start. Okay, so maybe I'll just sketch how the proof will go. So again, there are these phases. A phase starts when we unmark everything and bring in the new guy. and a phase ends when it's about to happen again. Okay? So we'll break the access sequence into phases. Within a phase, we'll call a page clean if, so let me not say within a phase, but at a given point. So at a given point in time, at a point in time, page is clean if it was not accessed in the last phase and also not yet in this phase. Page is stale, on the other hand, if accessed last phase, but not yet this phase. And the thing we're going to actually show we'll show that if there are we'll show that if there are L clean accesses in a phase, then opt pays at least L over 2, and mark for M pays at most 2 LHK in expectation. And then when you sum up over phases, you get that mark will be HK competitive. I slightly am lying because there's going to be something that has to be added and subtracted here, but it's going to telescope over all the phases. So this is really the thing that's going to matter. But we'll see that next time, I guess.